Hopefully you recognize this problem. This is the one that we did in the last lesson, where we were given this ball thrown upward at a velocity of 80 feet per second, and we had that same equation. And we did A and B yesterday. Today we're doing part C based off of this same situation. So take a moment, write down the question for part C, and then we're going to work it through together. All right, so in terms of like scheming, planning, how am I going to actually approach this problem? I know it's asking me for velocity. Well, remember before we did in fact figure out what the velocity equation was. We figured out in the previous parts that v of t equaled 80 minus 32t. Okay, so we know the velocity equation. Now, is that enough for me to go on at this point, or am I going to need to use something else? Well, for the velocity equation here, of course, velocity is what I'm trying to find, so obviously I don't know what v is already. Do I know what the t value is? Do I know what t is when it hits the ground? Not yet. No, not really. There's some ways we can kind of reason it through from previous work, but we haven't actually necessarily found it yet. So really then that's the question that you should be asking yourself is how do I figure out the time when it hits the ground? And for that we can actually go back to our original equation. The original S equals 80t minus 16t squared. It's just in order to figure out t, I got to plug something in for S. What is the position? That is, what is the height of this ball when it hits the ground? 0. So it's basically telling us plug 0 in for S and then to solve that for t. All right, so let's take a look at how we go about solving it. And there's really two main methods that I tend to see people do on this one, and it actually is well worth taking a look at both of them, because something weird can happen with one of them, and I just want you aware of it. Because one very common method I see is I'll see people move the t and the t squared to different sides. So, for instance, if I move the 16t squared to the left-hand side, and then when they get here, they're like, okay, well, I got t squared on one side and I got t on the other, so I can go ahead and divide both sides by t. And when we do that, we do end up with something nice and neat. 16t equals 80, so I can go ahead and divide both sides by 16, and I got t equals 5, which actually is the correct answer in this case, but we're kind of lucky, because there's actually another possible solution. It's just that the other one isn't the one that we're looking for in this case. If I actually solve this with a different method, I think actually I would dare say a better method here, I would actually start by factoring that equation on the right-hand side. And yeah, we could factor out 16t, but I'm even just going to illustrate just with the t here. I factor out t, that leaves me with 80 minus 16t. And so then, since I'm solving two things that are being multiplied, but it's equal to 0, I'm basically solving when t equals 0, which is when t equals 0, and I'm solving when 80 minus 16t equals 0, which then we can solve and we find that t equals the 5. So notice they both give us the answer of 5, but only the first one, I'm sorry, maybe I should say the left one here, the one that I just did, only this one also tells us that t equals 0. Which would make sense, because that would be like the point when it was originally thrown up into the air. It was thrown from a height of 0. And so it was thrown at time equals 0. But why didn't this one give us that answer? It's because of this line here, where we divided both sides by t. That only works to divide both sides by t, provided we know that t cannot equal 0. Because notice that if t equals 0 and then I divide by 0, bad things happen, right? The universe implodes on itself because we divided by 0. We can't do that. So if you're going to try to do this whole thing where you divide both sides by the variable, you have to know that it's not 0. Now, and in this case, we didn't know that, and it turned out to actually cause us some problems. So instead, when you see these types of problems, factor, because it helps prevent that particular error. All right, so now that I know that t equals 0 and 5, I wanted to know, remember, when it hits the ground. So that means I'm only interested in the second one, because the first one was just when it was first tossed. So now what do I do with the t equals 5? Plug it into velocity. Yep. So I'm now going to figure out what is v of 5. So go ahead and plug that in, figure out what it equals. And before we get that exact number up here, what would you expect your v value to be? Would you expect it to be positive or negative here? Negative, yeah, because this thing starts traveling upward, and then it's traveling downward when it hits the ground. And so if it's traveling downward when it hits the ground, that means our velocity must be negative. And so, yeah, we're hoping to see a negative answer here. If not, that tells us go check our work. But yes, we actually do get a negative number here. It actually gives us a negative 80. Negative 80 what? Did you remember units? If we're talking about a real-world problem like this, make sure you include the units that you were given. In this case, we are told up front that the velocity is measured in feet per second, so we include the feet per second. All right, so in this problem, of course, you want to make sure you write down the problem because it's really going to be the context of this that tells us what to do that we're going to be interested in. If you just write down the equations, not going to be all that helpful for you, so you write down the original. And then we have to start thinking about what do we do with all this information. So it's asking for the rate at which the area within the circle is increasing. So we got a couple of things there. We got a rate that's involved, and we got an area. Now, area is something we can actually go to fairly quickly, or at least I hope we can, because we're talking about a circle. We can actually figure out what is the area of the circle. Remember the formula? Area of a circle equals pi r squared. Yep. So our area equals pi r squared. Now, if I take the derivative of this, though, let's think about what that would really mean. If I take the derivative of this function as it's currently written, yeah, a prime would equal 2 pi r. Hey, that looks familiar. So the derivative would equal 2 pi r. But what would the units be? Well, our original area units are like square centimeters. If I do the derivative here, that's with respect to r. That'd be like square centimeters per centimeter. That's weird. That's not quite the rate we're looking for, right? Our rate that we want here should involve the time, because we're actually told what's happening per second up here. So I want a rate that can actually communicate how fast is it changing per second. How much is the area increasing per second? So that means we now need to actually take our area equation, and instead of figuring it out in terms of r, we need to put it in terms of t. So that means I need to write a new equation. What does r equal in terms of t? So like if you know 3 seconds there. If it's been 3 seconds, what's the radius? Well, it's got to be 180 because it's increasing at 60 centimeters per second. That means we did 60 times the number of seconds. So r equals 60t. That then allows me to combine these two equations. I can now combine them into a single equation that will give me the area in terms of time, which is what we want. Because then we can take the derivative with respect to time, and it'll actually give us a rate with respect to time. So a of t equals pi times 60t squared. Now, my next step is that I am going to need to figure out what the area derivative is. So I'm going to have to find the derivative of this function, but I actually have a couple options here. I could take the derivative from it as it currently stands, or I could actually square the 60t and find the derivative from there. Which one do you think is easier? And if you're not sure, envision what it would look like after you squared it. I'll actually write it out here. If we square that out, we would get 60 squared. Okay, 60 squared, hopefully you can do that in your head, because 6 times 6 is 36. And then, since it's a multiple of 10, gives us a multiple of 100. Pi times t squared. Which one of those seems easier? Well, different people look at things different ways, but to me, this second one seems a lot easier. Because in order to find the derivative of the second one, we're just going to use power rule. Whereas the previous one would require power rule and chain rule. All right, so then let's go ahead and figure out then, what is a prime of t? Find that derivative then. Now I'm going to use the second one because I thought that was a lot easier to use. So I use power rule. That means I multiply the constants out front. And notice, all of this is constant. It's not function, so I don't have to use product rule here. So I'm just going to multiply that by 2. So that gives me 7200 pi times t. Now I have my derivative function. I have some function where if I plug in any value of t, it will tell me how is the area changing. It's the rate of change of the area. So let's go ahead and use it then, because now we can answer our questions. How much is it increasing after 1, 3, and 5 seconds? Now, when we just do those calculations by plugging those values in, this is what we're looking at. 3600 pi, 21,600 pi, and 36,000 pi. But something's missing from each of these answers. Units. Yeah, how would 1 second be 3600? For some reason I got that 3600 stuck in my head. That should be 7200.
Half a second.
So there we go. We plug 1 in for t, we should get 7200. I just was looking at the equation up above it. All right. And yes, I did write them all in terms of pi. If you calculated it out, that's perfectly fine. But I figure if I can leave it in terms of pi, I like to. All right. But let's talk units here. So the original area function, what would the area be measured in for these? Well, we're talking about centimeters here, so that the area originally must have been measured then in square centimeters, or centimeters squared. You could say it either way. But now I'm looking at the rate of change. I just took the derivative with respect to t. That means that my rate of change is square centimeters per time. And time here is seconds. So it's square centimeters per second. So notice what this then is telling me. It's telling me for each of these that my area is changing by that many square centimeters every second when you get out to that point on the circle, which happens after t amount of time. So it's actually given us the rate of something useful per second. And that's what we're looking for. And in fact, that's going to be the big theme of today, is dealing with equations and being able to get derivatives that result in some sort of a rate that's in terms of time. Because that's actually how derivatives come up most, and how rates come up the most is per time. So I want to go back to the idea of implicit differentiation before I introduce today's totally new concept, because there's a little bit of subtlety in what we've been doing that we haven't necessarily thought that much about, especially because of some of the ways we've tried to make our lives a little bit easier. If I were just finding the implicit derivative of this, remember that we assume that the implicit differentiation means that we've been finding the derivative with respect to x. We just always assume that if it's x and y, we're taking the derivative with respect to x. Which means that when I go and find the derivative of y squared, it gives me 2y times y prime, the derivative of y, because y was a function of x. But for today's work, rather than writing 2y prime, I'm going to write it out the long way for a reason why you'll see here in a moment. So I'm going to write it as 2y. Remember that y prime just means dy over dx. That's that long way that we write it. We tend not to like writing it that way because it looks messier. It looks like all of a sudden we've introduced a whole lot more letters and a fraction into our problem, even though that means the same thing as y prime. And so we just wrote y prime for all of these weeks that we've been doing it because it's so much simpler. All right, and then from there we would take the derivative of the x squared. And so that was always really easy because it was just 2x. Now the reason why it was so easy for us to do that is because, remember, we're finding the derivative here with respect to x. Technically speaking, what I could actually write in here so that it was kind of symmetrical with the idea of what we were doing to y is I could actually say that I'm then taking the derivative of x with respect to x. There's like this weird little x prime term in there, and it's still going to equal 0. But what's this whole dx over dx thing? Well, it's x prime, but we're taking the derivative with respect to x. So what does dx over dx actually equal? 1. That's why we haven't had to write it. And it's been silly to say every time in your work, I want you to write out 2x times dx over dx, because that's just a lot of unnecessary writing for something that's going to disappear every single time. And so we just were able to leave it out. Well, today, we're adding a layer. Remember in that last problem, what we were really interested in is how is it changing as time changes. So let's take a look at the same equation and see how we would take the derivative of it with respect to time. This is the point at which you definitely want to be writing down this problem. And for a lot of people, when they first see this, this is where all of a sudden it twists their brains just a little bit. Because I'm now asking you to find the derivative with regards to time, and my equation does not include time. But what you're going to end up finding is that after we practice a few of these, you're going to find that we're going to be doing problems, and it's going to ask us to find out how fast is it changing. Like that problem with the circle. How fast is it changing over time when I'm told part of the rate? You know, if the radius is increasing, how is the area increasing? That sort of thing. These types of problems are called related rates for that reason. If you know one rate of change, how can you figure out what the other rate of change is? All right, so let's see how I would find the derivative of this problem then with respect to time. Well, most of it feels very similar. So to find the derivative of y squared, it's still going to be 2y times the derivative of y. But remember, I'm not taking the derivative with respect to x this time. So instead of dy over dx, it is dy over dt. Because when I write dy over dt, it means that I'm taking the derivative of whatever this thing is on top with respect to whatever this letter is on the bottom. So this means when I say dy over dt, it just means the derivative of y with respect to t. Or in other words, how is y changing as t changes? And so then that's where this gets a little bit more complicated though as we proceed into x. Because the derivative of x squared is no longer 2x. Because I'm not taking the derivative with regards to x now, I'm taking the derivative with respect to t, so it has to now have that dx over dt written in it. And why do I have to write it? Because it's no longer dx over dx. It's actually different on the top and bottom. So I still have to have that in there. And then on the right-hand side, the derivative of 15, it's still 0. Regardless of what the variable is that we're taking the derivative of a constant is still 0. Now, how do we then give our answer? Well, for the moment, this is it. Because you'll notice that there's two different derivatives given in this particular problem. We have both dy over dt and we have dx over dt. When we go and do these types of problems and we're actually solving story problems based on these, word problems, stuff that's in real world contexts, we're going to need to know at least one of those. Like in the problem that we just did before with the circle, we actually knew what the rate of change was for r. So it's like we knew this one and we're solving for the other one, that sort of thing. And so in these types of problems, when we actually do them, you're going to know what y equals, you're going to know what x equals, and you're going to know one of those derivatives with regards to t, where it's either dy over dt or dx over dt. You'll know one of those rates of change in order to actually solve these. So because of that, we don't solve past this. You don't have to do any extra algebra. Just find the derivative implicitly, call it good. So here's two new equations. I want you to practice this idea. Go ahead and write down both and then see if you can take the derivative of both of these with respect to time. At least take them as far as you can on your own, and then we'll work them through together. All right, so let's go ahead and find our derivative of the first function there. V equals x cubed. Looks like we're finding the volume of a cube here based on the equation. So I want to find the derivative with respect to time. So on the left-hand side, that means the derivative of v with respect to time. So that's just going to be dv over dt. Because remember, that means the derivative of v with respect to t. That's all that means in that notation. All right, now we got to do the derivative of x cubed. Now x cubed, remember, is no longer being taken the derivative of with respect to x. It's t. So that means I'm using chain rule. Just like I've always done with y being in an equation, I had to use chain rule because y was a function of x. Now x is a function of t. So to use chain rule, I do the derivative of the outer function, which is going to be 3x squared. So far the same, but then times the derivative of the inner function, which is x. So then I have to multiply it by dx over dt. And then that's it. We can go ahead and call it good right there. You're done. You don't need to solve for anything else in this case. All right, now the next one over. This looks like a surface area equation. So SA does represent just a single variable. I prefer just one letter for a variable, but hey, surface area they tend to use two, so we'll go with it. So then, if I'm going to find this derivative, on the left-hand side, it's just like the volume. It's going to be dSA, because I'm taking the derivative of SA, over dt, because I'm taking the derivative with respect to time. So t's got to be on the bottom. All right, then let's go ahead and take the derivative on the right-hand side. And so, on the right-hand side, again, r is some unknown function of t here. So I'm again using chain rule. So derivative of the outer function, something squared, that's going to be 2 times the 4 pi. Well, 2 times 4 pi gives me 8 pi. Come on. There we go. And then I subtract 1 from the exponent, so that's 2 pi r. But I'm still having to use chain rule, because again, it is that function of t. So then it's times dr over dt. All right, now in the past, whenever we've had to write like dy over dx, we've always simplified dy over dx. In fact, this is worth writing out, dy over dx. We've always simplified that as y prime. Y prime just meant derivative of y. That's all that can tell us. It doesn't tell us what it's with respect to. It's just everything we had dealt with before was always with x, so it wasn't a question. So now, on a problem like this first one on the left here, instead of dv over dt, would it be okay to write it as v prime? Would that actually mean the same thing? Yes, it is. It means the same thing. And in the long run, I expect most of you are probably going to go to that. You're going to go to the prime notation. The problem is that prime notation doesn't tell us what we're taking the derivative with regard to. It doesn't tell us if it's x or t or what. So at least for today's work, that is both the in-class work that you just wrote down and the assignment that you're going to get here shortly, I'm okay if you write it in terms of the prime notation. But I would like you to please first write it with the d over d notation. So that way we can kind of ingrain and build in the habit of remembering that even though those two lines are equivalent, I need to remember that it's actually the derivative with respect to t and not let that get mixed up.